Wow, all right. If you need to get a hold of me, there's my email address, and that's also the AAVSO.org is our website address, and just about everything that I will talk about here will be showing up on that website. All right, so I said I was an amateur. I think I had 5 telescopes as an amateur. Started out with something off of a Popular Mechanics ad. Progressed to building my own 6-inch telescope. And then I ended up with something that I actually have seen out here, which is the Dynasto Criterion model. It's a 6-inch f8. This fellow at RTMC was actually making models of these things, which is pretty cool. I wish I could afford to buy one. And on this telescope, I actually used this Tasco 2.4-inch 60 millimeter as my guide scope. When I went off to college, this got sold because it was way too heavy. I kept this and used it for solar work and things like that. So they actually did have some value. And then I got rid of that and I moved on to 2-meter telescopes and 4-meter telescopes and 8-meter telescopes. And some of the more recent projects that I've been doing at AAVSO are using 60 millimeter telescopes again. So I'm on the full circle. So, how many of you have observed this celestial body? All right. There's a lot you can do with the moon. Now, I'm talking about variable stars, but I just wanted to mention that there are lots of ways in which you can sort of do citizen science. And one of these is, you notice that this is a crescent phase of the moon, and you can see the Earth-lit side of the moon. And there are actually a couple programs run by AAVSO to look for lunar impacts on this. You use a video camera, and you just sit there and look at the dark side of the moon. And if you have multiple sites, you can actually correlate them and make sure that a flash that you see on there was actually detected in both sites, and so therefore it's probably real. And this tells you the impact history of the moon, at least to the current impact history. That also tells you the impact history of the Earth. So there's a lot of interesting science that you can do. The other thing you can do, I don't know you can see it very well. These pictures never show up. There's a star there, and there's a star there. Obviously, the moon is moving through the star field, and it moves through a swath of sky that's about 10 degrees wide and 360 degrees around. So you're talking something in the order of 3,600 square degrees. And that means that eventually it passes over lots and lots of stars. And you can look at those stars as they go behind the moon's limb, and you can learn something about the system. If it's a binary star, you can actually see the light decrease as the first star gets occulted, and then you see the light decrease as the second star gets occulted. And that's a way of looking at very, very close binary stars, things sort of sub-arc second separation that you can't do from the ground. So lots of neat things you can do with the moon. Like I said, lunar impacts. Most of this is being done with video cameras today. This is another object. How many of you have actually seen Pluto through your telescope? All right. I think if you have really, really good seeing, that you'd be able to see Charon through your telescope too. And that's because the separation between these two is on the order of an arcsecond at best, sort of. If you had really good seeing and you caught it just at the right time, you can actually see both. Charon actually was discovered with the 61-inch telescope at the U.S. Naval Observatory where I work. And so this was kind of a pet project of mine when I was in graduate school, was to learn everything there was to know about Pluto. At that time, it was easy. Today, it's not. So here's the orbit of Pluto. Pluto actually goes around. It's the very center of the system that includes Charon and a couple other satellites. And the orbit of Charon itself, like I said, is on the order of an arcsecond away from Pluto. You'd never be able to see the fainter satellites that just way too faint. Hubble has trouble with those. But it'd be fun to do that. I like to do that. But you can actually watch Pluto occult stars because it moves in front of stars just like the moon does. And by doing so, you can determine a lot about Pluto itself. You can determine the size of Pluto. You can look at how it goes into eclipse and then back out of eclipse, and that tells you something about the atmosphere of Pluto. And you can also look for other fainter satellites that might be going across the star at the same time. These are all things you do with photometric techniques. You're looking at the brightness of the system. This is the old one. How come I got the old presentation? Did you pick the one up off of Arne?
Should have been. You want to try to get your new one?
Let's see. This one I can do all right. I think I'll just pass over a few slides. Let's just go ahead and do it. We're already behind time. All right. So I want to give a commercial before I get started, and that is about the American Association of Variable Star Observers. It's one of the oldest citizen science organizations in the world. There's one that's older, which is birding group looking for the migratory paths of birds. But as far as variable stars are concerned, it's the oldest. It's also the largest. We currently have about 1,000 members in 45 countries. And one of the reasons I'm giving a presentation here today is the fact that we're celebrating our 100th anniversary this year. In October, we will have a large meeting down in Cambridge, and you're all welcome to come down and celebrate with us. We have about 3,000 members worldwide, and currently our database of variable star measurements is about 20 million coming in from all amateurs. And it was born during the last great era of sky surveys. These were done with photographic plates back in the turn of the century, 1900 to 1920-ish or so, and it was primarily done at Harvard. And so that's why our organization started in collaboration with Harvard. And what they were doing is photographing the sky, both northern hemisphere, southern hemisphere, and they were finding all kinds of stars that varied in brightness. They didn't have enough time to study them themselves. They enlisted the aid of amateurs to help them out. And what's interesting to me is when you look at all the telescopes that were in the Harvard Sky Patrol, to me they look like they're almost all handmade, and they were of varying sizes and quality. I mean, this one here is a 1-inch lens that was used for photographing large areas of the sky for bright objects. And then they went all the way up to the 20-inch Metcalf, which was a really nice refractor, 20 inches in diameter refractor. That started at Harvard initially and then went down to South America, continuing to survey the sky. But they used a lot of very primitive equipment in those days. And they took photographic plates. All the photographic plates are sitting in Harvard College Observatory in what's called the plate stacks. And there's, I don't know, Ed is probably, if he's in here, he'll tell me how many there are. I think there's about 600,000. And they're all sitting in these manila envelopes, and they're currently in the process of digitizing them. And what used to be done, though, in the turn of the century, was somebody would actually take one of these plates, put it on a light table, basically, and go and measure the brightness of a star with respect to stars that in the vicinity that were also recorded on the plate. And you come up with what's called a light curve. So here is basically time this way and brightness going this way of a particular star. And what they're trying to do then is to find out what kind of a variable star it is, whether it's a pulsating variable or eclipsing binary or any of the other varieties there are. And you have to do lots and lots of observations. Each one of those data points on this plot was a hand-eye observation where they recorded it off of a plate, measured it carefully, and marked down what the measurement was. The amateurs that were involved were mostly Bostonian lawyers and doctors and things like that, people who could actually afford telescopes in those days. This is Alcott's private observatory, which was attached to his house, much like Mario Mata's observatory today, but a much smaller telescope. This one is about a 6-inch refractor, if I remember right. Some of the other early observers were using very similar kinds of equipment. This fellow here was actually an Italian who joined the organization very early on. And they were taking observations of various kinds of stars that the Harvard College Observatory professional astronomers have discovered. And here are some of the light curves that they came up with. You can see that this star sort of comes up and does this repetitive cycle. And the period here is on the order of 3 years that this data was taken. It went all the way from 3rd magnitude down to 10th magnitude. This is Myra itself, the very famous variable star. Some of the other variables, over the same period of time, had many pulsations, many cycles in their variability. And you can get into some very weird stars. This is about 30 years worth of data on what's called a cataclysmic variable, but it's a very unusual one in the sense that it sits there and goes into outbursts many times, but then every so often it just sort of sits at one brightness level. And then it goes back and oscillates for a while, and sits at one brightness level. And so these are kinds of stars where it took many years of observations before you could actually determine what kind of a variable star it was. The original headquarters for the AAVSO was in Building A, which is this one. This is the big 15.5-inch refractor that Harvard College has. This building no longer exists, and that's one of the reasons why the AAVSO moved to different headquarters. These are some of today's observers. So I showed you pictures of what the old style observers look like. All men dressed up in suits, and I think they actually observe that way. At least I got the pictures taken that way. But that's not the case anymore with the amateurs. As you see the telescopes that are sitting out here on the lawn, you can range anywhere from this kind of a telescope, which was a Dobsonian in bowling ball shape. This is Mike Linnell, who's in Hawaii. He has a 20-inch telescope that he sets up every night and observes. To telescopes that are commercially available, but they're hundreds of thousands of dollars. So you can find a wide variety of people who are using telescopes today. All these people are contributing variable star observations. Headquarters for the AAVSO is in Cambridge, Mass. It's about a mile away from Harvard College Observatory. So the goals of our organization are multifold. We archive all new observations that amateurs are making. We look for all the historical records from various groups such as the British Astronomical Association and so on, and try to incorporate those observations into our database. We do a lot of training, so we have manuals that are available if you want to learn how to do variable star observing, either with visual observing or photoelectric or CCD or any of the other techniques. We have a manual that allows you to do that. We also hold various workshops in conjunction with our meetings. And then we do our own research with some robotic telescopes that the AAVSO has. And if you are a member, you have access to. And like I said, we have about 20 million observations. It's just increasing. And one of the reasons why people get interested in looking at variable stars, well, if you look at all the fuzzies in the SDA catalog with your telescope, you pretty well say, okay, well, what's the next step? I can go and look at M51 again, or maybe there's something else I can do with my telescope. And one of the things that people tend to concentrate on when they first start looking at things like variable stars are the Myra variables, which are long period variables, typically periods of like a year or so. And what they are is a big red star that is pulsating, so it changes its physical size. And so it changes its brightness at the same time. It takes about a year to do this. And when it does it over a very wide range in magnitude. So it goes from, say, 2nd magnitude to 10th magnitude. That means that it changes over a period of a year its brightness by 8 magnitudes. And so it's really easy to follow these stars. They're nice and slow. If you only get to observe once a week or something like that, then It's easy to take in a measurement, and the next week you get another measurement, but it really hasn't faded that much or brightened that much. And so you can actually make a light curve of your own observations. But the real thing that people like about the Miras is that they're red stars, and so they're little jewels in your eyepiece. And if you look at almost any field of view where you have a red star, it's going to be probably one of these long period variables. So they're just lots of fun to look at, and so people tend to adopt particular stars. But at the same time, making a measurement of its brightness is a scientific measurement. You're using your human eye as a detector. Like I said, we have robotic telescopes scattered around the world. Here's where they are currently. And here's an example of one of the telescope systems that's CTIO. It's a pair of 8-inch telescopes that are surveying the sky in the southern hemisphere. So the next 100 years, what we see with sort of the scientific contributions coming from amateurs is that we're entering the next phase of surveying the sky. And it's being done by these reasonably sized telescopes. This is Pan-STARRS, which is about a 1.8 meter telescope. But the big change is that they're paving the entire focal plane with silicon detectors, CCDs. And you can see the size of the camera that's being used. This is the entire array of CCDs that Pan-STARRS, for example, is using. Pan-STARRS is primarily trying to find all the near-Earth asteroids, but as one of the side benefits of it is that they're finding lots and lots of new variable stars, which of course they can't follow up. So again, the aid of the amateurs is necessary. This is another one in the southern hemisphere. This is Sky Mapper. Mike Bessel, who is an astronomer down at Siding Spring, is bringing up this 1.3 meter telescope, again a very wide field, again primarily to survey the sky at an infrequent basis. They need more observations to find the characteristics of the stars that they discover. And the big one, which is coming up, is LSST, which stands for Large Synoptic Survey Telescope. This was the top-rated project in the recent decadal review for professional astronomy, and so it's currently being funded and starting construction. They already have some of the mirrors for it, and this will go down at CTIO, actually at Cerro Patron, which is the mountain in the background of that pair of twin 8-inch telescopes. And again, we'll survey the entire sky. And this is the size of its focal plane with sort of a model of what the the moon would look like. Yes, it is the moon in that field of view. So it's about, I think, 10 square degrees per image that we take. And then finally, Gaia, which is going to be launched in 2013 or thereabouts, is another survey instrument. So basically what's happening is that we're entering into this era where there's a lot of professional interest in surveying the entire sky to look sort of at the statistical nature of the sky. How many R-Lyras there are, how they trace out the spiral arms or the halo of the galaxy. And they're finding all these sort of common everyday stars, but they're also finding lots and lots of transient variables that need follow-up. For instance, LSST, they're predicting is going to have about 1 million transient objects, things that have changed in brightness from one night to the next, every night that they're going to report. And what they're trying to do is find ways in which they can filter this down to a handful of objects that the professionals can go and look at. A lot of this can be done by computers, but you get down to the point where humans have to be involved, and that's where amateurs really come in handy. So that's basically everything I was saying. The other area that you're finding with these surveys is that they're using bigger and bigger telescopes, which means that they're looking for fainter and fainter things, but they're doing it with sort of fixed exposures on each view of an area of the sky. And that means that they can find all the faint things, but because of the CCD dynamic range, they saturate on all the bright things. So quite often what will happen is that they'll get a transient, something that wasn't there yesterday, is there today, but it's too bright for the system, it's saturated, and there's no way that they can follow up themselves. They need to have outside help to help out. So where can amateurs help? It's the fact that you have this neat parameter space. And that is that you can look at things that are brighter than what any of these surveys can do. You can look at them faster, so you can look at them every night, and 3 or 4 times a night if you want to. Professionals are actually now making use of the innovative technology that's available through the commercial market for amateurs. So the nice go-to telescopes and CCD cameras that you can buy off the shelf, professionals are actually starting to use those. We used to have to build these cameras one at a time. And so one of the CCD cameras I was using at the U.S. Naval Observatory, for example, has a 2K by 2K sensor in it. And that camera costs about $135,000. And now you can go down and get something with more pixels in it from SDIG or Finger Lakes for just a small fraction of that cost. And so professionals see this and they're doing something with it. So why should you, as an amateur, observe? Well, like I said before, you may be tired of observing the same old things. I'm not. I mean, when I come out here and I get to look through a telescope, I get to look at M13 for maybe the 14th time instead of the 400th time. Because as a professional, I hardly ever get to look through a telescope. And that's why it's really fun to come to sky parties, because people set it up, they know where to point the telescope, which is a good start, and then you actually get to see through it. But when you go to the observing field and everybody's looking at M13, it'd be kind of nice to look at something different. So sometimes looking at double stars and looking at a really bright variable is a nice way to sort of go to something different. And you may feel that you want to contribute a little bit to science. So you want to take an observation, you want to use your time, but you actually want it to be used in research. And you can do that with variable stars. It's hard to do that with almost any other branch of science. You may want to do your own research. There are people who like the whole process, from taking the data to analyzing it to writing the publication, and you can do that as well. There may be peer pressure in that the guy next to you is observing a variable star and he estimates its brightness as being something, 10.5. And you then may feel the need to go and look at that same star and see whether or not you get the same measurement of brightness or whether you screwed up. You also get to meet a lot of new friends. Now, the people here in this audience, I know a few of you, but not very many. And if you started doing variable star work, it would reverse. You would start going to meetings where you meet lots of new people rather than the people that you see every time you come back to Stealthing. So it broadens your horizons. You get to see some different kinds of people. And you may be interested in variable stars just because you've seen one. You look at M51 and you saw this great supernova that's going on out there, and you're just interested as to what is it, and why is it so bright, and why is this one bright and the one in M33 wasn't as bright, and things like that. And then you just might want to do something fun. And I like to look at variable stars because I think they're a lot of fun just to watch something that actually physically changes in the sky. We have a mentor program that will help you get you started. So, to do variable star observing, here's a little checklist of how you go about it. And the first of these is that on our website we actually have lists of interesting stars. Stars either that are currently targets of campaigns because somebody's looking at with HST at some cataclysmic variable and they want to make sure that it isn't an outburst. And so they're asking for observations from amateurs. So there are ways in which you can find stars that are of interest to others. There's also several lists on our website of stars that are easy to observe, or stars that are long-period variables, or young stellar objects. And so starting with our website is a good place. Once you decide you have a star that is of interest, it's going to be up in the sky tonight, then what you need to do is to create a finding chart for that object so that you can look through your telescope and find it, or look with your pair of binoculars and be able to star hop and find the appropriate field. Then you need to find the target and local comparison stars. These are stars whose brightness is known, that you're going to compare your target against this set of stars to find out how bright it is. And that is the hardest step, in my mind, is finding the target that you're interested in, finding that variable star in the sky. It's easy to find the right constellation, but if you're looking at for a 14th magnitude object, like trying to find Pluto for the first time, it's really tough. But once you get beyond that step, then everything else falls through real easily. And as a matter of fact, on the back table there, I have a list of sort of 10 really easy objects to look at. It's called our 10-star training tutorial. And next to that is another list, which is called the analysis tutorial, which has about 5 stars in it for more advanced operations. You're welcome to take any of those that you want, as well as our brochure in the back. And I'll show you how you go about making an estimate here in just a minute. So after you've made the brightness estimate for the star, you log into our website. You can register to get onto our website. It's free. We don't charge for anything to make an observation and report it. We ask that you sign up for an observer code. And the reason for this is that we have 20 million observations in our database. And for each one of those observations, we have a tag associated with that measurement that says that it was made by observer X. And we need to be able to identify that person 20 years or 50 years in the future. And we do that by assigning observer codes. So you go in there and you say that my name is so-and-so, I live at such and such an address, and in return you get this little 4 or 5 character observer code, which is based on your initials of your name, so it's a little bit easy to understand. But that is yours and yours alone. It's a unique code, it never changes. Anytime you make an observation, everybody knows exactly who made that observation, whether you like it or not. And then after you've gotten, so you're on the website, you have the observer code, you have the estimate of brightness for the star, you go in and use a tool that we have on the website called WebObs, or web-based observation submission. And it just has fill in the blanks for what time of day you observe, what the object is, how bright was it, and things like this. You click the button and it's into the database. And then you can actually plot the light curve for the particular object that you're interested in. If you're looking at Myra, for example, you can ask to see the last 400 days of observations of Myra, and it'll give you a little graph of those observations. You can highlight the observations that I've made, and it'll put little crosses on each one of those observations so you can see how your estimates compare with everybody else. And so you just do this and just watch the light curve as it develops. Now let me start off with visual observing, because that's the simplest and the cheapest. You don't need any extra equipment outside of your eyeballs. And you can do this visually. There's a couple dozen objects that are bright enough that you can go out and tonight measure the brightness of a variable star. Myra is one of those. When it does reach maximum brightness, it's second magnitude, so it's an easy star to see. Polaris is another one that you actually could measure, except that the amplitude of variation is too small for the human eye to detect. But it is a variable star. And so there's a whole series of these that you can go out and look at, even with your eye. You can then graduate to using binoculars. If somebody has a pair of 20 by 100s or something, you can go really deep. And then you can use your telescope in a visual way. So for instance, if you were looking at M51 tonight, and you see the supernova that's in M51, you can actually measure its brightness with known stars of brightness in the same field. And I'll show you that in a minute. Now, there are some drawbacks with visual observing. The first is that you can't go as faint with your eye as you can with taking a digital image. And you see that all the time with looking at dark sky objects, deep sky objects. In that if you're trying to take a picture of M51, you can go fainter with a 10-second exposure than you can looking at it with your own eyes. So you can't go as faint, but that still leaves you with tens of thousands of interesting objects to look at. Another one is that it's not a permanent record. It's not a picture that you've taken that you can pull up on your screen tomorrow or 2 weeks from now. You're making the estimate in real time, recorded in a book or something like that. And if you made a mistake, you transpose digits or whatever, you can never go back and figure out what you did wrong. And so that's one of the drawbacks of visual observing. But it's only a small drawback. Another is that the human eye is a remarkable tool in that you can look at full sunlight and you can look at stars at night. So you have this huge dynamic range that's helped out by the different size of your iris. It's also helped out by using by the adaptation of the eye as it gets fainter and fainter out, changing over to the looking at things with rods instead of cones. But because of you gain that huge dynamic range at the expense of measuring things very precisely. So the human eye can only see changes that are sort of on the 1/10 to 2/10 of a magnitude level. For a very high amplitude variable, like these long period variables, the Mira stars, 2/10 of a magnitude out of 8 magnitudes means that you got lots and lots of steps in brightness. So you get this great light curve. But if you're looking at an eclipsing binary that only changes by half a magnitude, then that means that your light curve is going to look pretty crappy. But if you combine your light curve with everybody else's that's observing it, what happens is that everyone observes it probably in a full-scale professional seminar conference dealing with the star, in which people will then present their information in addition to the amateur contributions, and will actually, maybe for once and for all, be able to decide whether it's the low mass scenario or the high mass scenario, and maybe get an idea of how the system formed. The problem with something like the low mass scenario where you're dealing with a evolved star is that these disks around stars don't last for very long. You get a disk around a star, it tends to dissipate after a while. So why is the disk there in the old star configuration? The young star configuration, that matches, but then some of the other features don't match. So I don't know what the answer is yet, and I think it's going to take some tweaking of models. In the meantime, we do need more data. So if you can think about observing the star, go over to the Citizen Sky website and sign up and start taking some data and contributing to the project. Epsilon Aurigae is just coming around the sun. It's usually July is the month that everything goes away. And now you can start seeing it in the early morning hours from our location. Like I said, any of the types of observations that you can make will be valuable and useful. And if you want any more information, here are a couple of websites. The Citizen Sky one, the AAVSO one. I said that Jeff Hopkins is running a campaign, and he does put out a newsletter of some of the more recent observations. And so here's his website and his campaign. I think if you Google on Jeff Hopkins and Epsilon Aurigae, this will pop up. And then, like I said, we're going to have a special issue of our journal, probably August of next year, in which we will have at least the amateur contributions to this project. And hopefully we'll get some professional papers in there as well. So that's all I have to say. I'm sorry I can't give you a good answer at this point, but it really is a fun system. Thank you very much. Has there been any spectroscopic deductions regarding things like the chemical composition of the cloud? The trouble with the cloud is that it's dark, and so it's not emitting any light of its own. So the only light that we have is either from reflection from the V star in the center, or we actually do see some indication of heating on the trailing edge of it as the cloud passes beyond the star. It is rotating on itself, and you can actually see it get heated from the F star and then rotate into our line of sight. And so we get a little bit of information, but it's just not enough to know more than green size, and that's about it. Any others? Yeah?
I may be displaying my ignorance, but has anybody thought about the possibility that the black cloud is actually forming another star?
So, has anyone thought about the possibility of the black cloud forming another star? Like I said, if you go with a high mass scenario, then you're dealing with a young stellar object. And so whatever is being formed in the center probably is still being formed and hasn't gotten down to the main sequence yet. So in that sense, yeah, there's a possibility that something is getting formed in the cloud. One of the problems there is that if you assume the grain size as being very large, that's kind of counter to what most people think is a protoplanetary dust cloud. They tend to have small grains. And so, you know, there's pluses and minuses. I think it would be a neat scenario. But the problem with that is that if it's a high mass F star, then there has to be a high mass object inside of the dust cloud. And if it's a high mass object in the dust cloud, how come we don't see it? And so, you know, it's a mystery. And so it's a fun one. That's why so many scientists have been looking at it and trying to figure it out. Here's a third magnitude star, and we don't know what it is. And so, you know, if you look at that, then, you know, you just wonder about some of the other things that we have put so much time and effort into. Here's something that anyone can look at, and they ought to. Are there any other systems that are remotely similar to this? I think I've heard of one, but I don't remember the description offhand. Let's put it this way, it's an extremely rare object if there are any that are similar to it. And I don't think I know of any, certainly none that have, you know, this kind of period and everything. I know of other systems where there is an accretion disk around them, but it's nothing like this. Okay, well, thank you very much.